noon, morning, evening, whenever you're viewing this, I have no idea. It's evening for me. Not going to tell you what time. But anyway, let's look at this problem. So there are a few important concepts to think about when it comes to this problem, right? And the idea is that we are, first of all, not given any numbers. So everybody loves a question in which there are no numbers, of course. But the ultimate principle to keep in mind is that when physics does this, and when physics gets purely symbolic, the way it is in this problem, that means that the guy writing the problem wanted to prove a point to you, okay? So there is a point proven in this problem, and we're going to dissect it. So I am aware that there is a way to do this problem with a double integral, and ultimately what it boils down to is the double integral kind of collapses into a single integral because you realize that part of this problem doesn't matter. So without further ado, let's take a look at it. First of all, we have our loop, right, sitting in this coordinate plane, or I guess 3-space you can call it. And I want to recall something. So first of all, of course, we have a magnetic field. We have an EMF induced in the loop as a function of time, as the problem states. And I'm just going to keep a formula for us to refer to. The induced EMF in the loop is going to be the negative of the change in flux. Of course, the change in flux, all that's really saying is, okay, well, the magnetic flux is how many magnetic field lines do I have for a given area. So you say B times A. And symbolically, again, this is just saying, okay, this is going to determine the density of the magnetic field at the location I'm looking at, and this is going to determine the area, right? So if we extrapolate the density and the magnitude of a magnetic field and apply it across a whole area, and if we know how that field changes, then we can talk about the magnetic flux. Okay, we've defined magnetic flux. So the idea is just physics principle here. If you change the amount of field lines that are going through a conductive loop like this, like let's say we have no field lines right now, suddenly I start adding some, right? Picture these as magnetic field lines. Then the consequence of that will be that a current runs through this loop to oppose that change. And in this case, to oppose the change, you would need field lines going down. Apply your right-hand rule. The current should be going counterclockwise. Oh, excuse me, clockwise. Okay. So that's how we take care of the direction. But as far as magnitude goes, well, that's sort of what this exercise is about. So the other thing about this problem is it is a neat introduction. I'm going to scroll up here. It's a neat introduction to the notion of several things changing, right? Because we're so used to, okay, well, here's your magnetic field strength, as a function of distance or something, and then, okay, integrate through to take care of that. But in this case, not only do you have to worry about the fact that, well, as I go out in a given direction, the magnetic field will grow stronger, but you also have to worry about the fact that these magnetic fields are essentially fading in and out in equal and opposite fashions. So in other words, when we're at a point where Cx cosine omega t I hat, and this cosine goes to 1, that sign for the other aspect, the other part of the magnetic field, has to evaluate to 0. All this says, and all this really means, is we're using trig functions to say when one field is at full strength, the other field isn't even there. And when one field is at full strength, the other one isn't even there. That's the idea. The fact that these are varying, and one has a cosine and the other has a sine, just means that when one blinks in, the other blinks out. And I say blinks, but really these aren't discrete appearances and disappearances. They're gradual, and that's what cosine and sine are really good at demonstrating. So we've talked a little bit about theory, and the idea, again, behind this problem is you're looking at this loop, and there's a constantly varying magnetic field and it varies as a function of time and distance, right? I mean, if we look here, okay, we have some constant. Great. Actually, let's look at the one up here, right? This is our formula, and it looks a little nicer up here. All right, we have a constant, okay? And then for the I hat part of the field, so in other words, if this is our coordinate axes, there must be a field pointing I hat. The magnitude of that field depends on your distance away in the x direction. So in other words, as I traverse and travel out in this direction, the density and the strength of this magnetic field is going to increase. Then we have the cosine term that says, well, okay, at some points in time it's going to be weaker, at some points in time it's going to be stronger, right? And that's in the I hat direction as we've drawn here. The other term here is, okay, that same constant is going to distribute into this part right here. Okay, well, as you go out in the y direction, say this is y, the magnetic field will grow stronger. And don't forget, this is k hat, so it's pointing up, right? So we have a magnetic field that points up in the k hat direction. This is z here. And we're basically saying that as you move out in the y direction, or in other words, j hat, as you move out into j hat, this magnetic field pointing up grows stronger and stronger. And again, it varies with time. So in other words, at some points in time, it won't even be there just based off of that trig term. It's pointing in k hat. That's what every kind of piece of this means. You have to pay very close attention to what symbols and letters are going to mean, because this is all just a very, very symbolic way of me giving a statement to you. And the statement is, okay, well, I'm going to have a very strong magnetic field, and it gets stronger as you go out in this direction. It's going to point that way, and it's going to appear and reappear, and kind of, its magnitude will increase and decrease as a function of time. And the same applies to this magnetic field as I go out in this direction, but wait, this field points up this way, and it is also going to be appearing and reappearing, and its magnitude will change sinusoidally as a function of time. So the idea is field here, and it has certain properties that are described by this entire formula, right? Like ultimately, the point here is not for us to trip everybody up. The point is to describe a physical phenomenon with a certain level of granularity, which is what this formula allows. Now, I know I've done a lot of talking and not a lot of problem solving, so without further ado, we can kind of dive in on what the approach here is. So, when I approach this problem, the first thing I recognized is, okay, well, this function tells me that I have some field going off in the I hat direction, as pictured, and I also have some field going off in the k hat direction. And of course, they're time varying, they're also distance varying, because as I move out in the x direction on this graph, the strength of the magnetic field increases. So in other words, at x equals 0, right there on the z-axis right there, or even down here at the origin, the strength of the magnetic field, the one that points in the I hat, is 0. It's just constantly 0, because if you look at our formula, well, you have a factor of x in there. So in other words, your position of x goes in here, and when you set x to 0, this whole thing evaluates to 0. Okay? And likewise, that factor of x tells us that as we move out that way, it'll get very strong. Okay, check. Same thing applies to the vertical magnetic field, or in other words, the one up here, the k hat magnetic field. It is pointing up, and it gets stronger the further away you move from the x-axis, or in other words, the further you move in the y direction. So, the magnitude of this field varies with the distance away from this axis, okay? And you also know that it's time varying. So what is the significance of this? Well, we can make it very dead simple right now and first ask ourselves, what is the flux through this loop due to both fields? Well, the flux through the loop due to the field shooting off an I hat, let's look at it from the side, right? Say that this is our loop sitting in the, this is the xy plane, xy, right? Our magnetic field is going that way. And if this is our area vector, then the angle between these two vectors is 90. Why is that important? Because remember that the flux of anything, and in this case, the magnetic flux can also be expressed as BA cosine of theta. And theta is the angle between our two vectors. Now our magnetic field vector is directly to the left, and our area vector is directly up, and that means that our angle is 90. Cosine of 90, of course, is 0. Significance of this is that at every location in this drawing, no matter what, you are going to get that setup. You're going to get that setup of a 90-degree angle between the area vector and, well, the normal of the area, and your magnetic field. So obviously and observationally, you can kind of intuitively come to the conclusion that if a field is going out that way, there is no way for it to go down or up through that loop. So that's the first thing to recognize here, and that's going to make our life a little bit easier. Now, the next part is the field that does go through the loop, and that is our other field described by that term right there, the y sine omega t. That tells us, okay, there is a magnetic field that goes up in the k-hat direction. And by the way, we're not really given any bounds on this. It's not like it's only confined to this loop. You know, there's a magnetic field out here pointing up certainly as well, and out there. But we are only concerned with the magnetic field, of course, going through the loop. That is what defines our magnetic flux. And furthermore, that's what's going to induce our EMF, because note that the conductive material, or the loop of conductive material, is what allows for that induced EMF to oppose the change in magnetic flux. So that's the idea here. And now we know that we have a varying magnetic field that goes up like that, right? And as you move away from the x-axis, it gets stronger. But another question that we have to ask ourselves is, right, the EMF induced is the change in magnetic flux with respect to time. And notice how this is, with respect to time, not respect to distance, which means that in order for there to be an induced EMF, this thing has to vary somehow with time. And we, again, are given that it varies sinusoidally with time. So the magnitude of this thing will go up and down and up and down. Okay, you'll have to ignore that. So here's the point, and here's what we get to. We have two things that are really changing and impacting the strength of our magnetic field. Not flux, well, flux by extension, but strength of B, and I'm going to say the one going up in k-hat. It varies with time by sine omega t. So in other words, whatever magnitude, whatever amplitude I have here, times sine of omega t will inform us how this thing changes with time. And we also have the distance component of it, because as we look at our axes, as we move off into the y direction, again, this thing is getting stronger and stronger. So how do we account for both of these things? Well, first of all, we want to look at the the magnetic flux as if time weren't changing, and that's just only for the moment. So first of all, we're given the expression, and we're only going to look at the k-hat component now, because as we talked about, we don't care about the i-hat component. We have c times y sine omega t in the i-hat direction. So that's our magnitude in the, k-hat direction. K-hat, right? So y, which says, as you move out in y, field gets stronger. Sine omega t, which tells us how it varies with time, and some constant times all of that. So that's the idea. Now, what do you do from here? Well, note, again, that through that loop we were looking at, right, if we look at this point on the loop, the magnetic field through that point it's relatively weak. We're pretty damn close to the x-axis out here. But, as we travel along this loop again, the field gets stronger and stronger and stronger. So how do you account for that? Well, here's what you say. You essentially say, let me integrate, right? Let me integrate a bunch of very thin rectangles so that I can scoop up and get all of those field lines and account for the fact that the field lines are getting stronger as I move out, right? So, of course, if I'm integrating an area, well, this area has to be made up of a length and a width in the case of a rectangle. And our infinitesimally thin rectangle here is going to be whatever the length of this thing is times some dy. We're moving out in the y direction, integrating through y. So dA must be 3 dy. Thin little rectangle, dy as a width, and 3 as a length. And you take that rectangle, integrate it through this whole surface, and it'll give you the net magnetic flux through there. Now, of course, it's the change in magnetic flux that we're concerned with, but we'll get to that in a minute. So, like I just said, we're concerned with the change in magnetic flux. So, how do we measure that? Well, in order for the magnetic flux to change, our area through that whole loop is constant. Constant. But what isn't constant is our magnetic field. Remember, our expression says magnetic field is Cy sine omega t. Okay, in the k-hat. So if we want to know the change in the field with respect to time, which will influence our change in flux, and by the way that's connected is, well, okay, flux is a measure of magnetic field through an area, and our area isn't changing, then if our flux is changing, the magnetic field must be changing. All we have to do here is take a derivative, right? We say, okay, omega Cy cosine, don't slip up your derivative like I did, omega t k-hat, this expression right here will tell us how this thing changes with time. And if we apply that change to an area, then that's how our magnetic flux, of course, changes with time. Have something to describe the magnetic field's magnitude, have the area, you have a flux, okay? Now, the next part of this is to deal with the fact that the field grows stronger as you go out in the y direction. Here's what you do. Okay, well, we have a loop that sits like this, and that's a B right there. It's a little hard to see. Okay, so we're going out from 0 to B when we're looking at that little rectangle. 0 to B. Then we plug in our expression for the magnetic field. Okay, omega y c, omega c y, cosine omega t, okay, then we have our A in there, our area. Now, remember, we're looking at dA, and in this case, dA for each of those little rectangles is equal to 3 dy as mentioned earlier. So we get a factor of 3 dy, and now, given that bound, we are allowed to take the integral. Okay, so to evaluate this integral, all you have to do is pull out all of these constants. Okay, well, let's pull out the omega, let's pull out the c, let's pull out the cosine omega t, and we're left with an integral, and of course a 3, 0 to b of y dy. And of course, when you take that integral, you're going to get y squared over 2, no plus c because we're in physics for now, and we go from 0 to b, which leaves us with b squared over 2. Pull down all of your other constants, 3 omega c cosine omega t, c cosine omega t, and you now have, and that's in parentheses, you now have an expression for the change in magnetic flux through this thing with respect to time. Okay, now the very last step here is to identify, all right, which direction are we going in? Because ultimately this is a magnitude, and I'm going to rewrite it just for clarity. 3 omega c cosine omega t b squared, and you can put all of that over 2. Okay, all right, so having found the magnitude of our induced EMF, right, now we can kind of start paying attention to the sign. And here's what's going on in this problem. Okay, so if we refer back to our original formula for the magnetic field as a function of time, the one pointing up in that direction, okay, we said it was y sine omega t in the k-hat direction, right? And this tells us that, okay, as time progresses, this magnetic field is going from up here to down here to up here to down here to up here to down here. So this is not only referring to the strength of the magnetic field, but also the direction, right? There are going to be points in time, like on this rising edge, where the magnetic field is very, very much positive, pointing up. But there's going to be other times during this time interval where it's going to be pointing down and negative with some other intensity. So the point is, this constantly changes from up, down, up, down, up, down, and when we refer back to our induced EMF is equal to the minus change with respect to time, change in magnetic flux with respect to time, if we look at a rising edge, if we look at a point in time in which the magnetic field through the loop increases, right, like this, then what has to happen in order for us to oppose this change? And by us, I mean the EMF. Well, here's one way of viewing this idea is think of that EMF as something that looks like an electric field that kind of encircles this loop and pushes the current a certain way, right? Now, if we want the current to oppose the change here, and we're adding field lines going up, then that means we want the current, or the current rather, wants to add field lines going down. Again, at a rising edge, at a point where the magnetic field grows stronger, the current will act in such a way to add field lines down the center of the loop and down through the loop. So if you take your thumb and point it in the direction of that down, then your fingers will curl around this loop clockwise, right? And what does this imply for us? Well, it implies that if we just used all of this math to derive a formula for the time rate of change of the flux, then the EMF must be the negative of that. The EMF and the current will behave in such a way that field lines are added to oppose this change, right? And it will work out. It will work out. If you have that negative and if you have the cosine there, just take my word for it. It'll work out well. And I'm sure that Professor Glenn would be open to exploring this concept a little more. But for now, trust the formula, and that's the idea. So, it's a bit of a crazy problem, and of course you could do this out with a double integral. I chose not to. I chose to just let the physics do the talking, and if you have any questions, send either myself or, well, send either Professor Glenn or myself an email. Definitely Professor Glenn first, though. He's the goat. All right, take care.